Okay, now, thank you. So we are ready to start. Thank you for choosing my talk about explainable, responsible AI. As you know already, I'm Marcin Szeliga. I started my career working with SQL Server, but a few years ago I transitioned to the cloud, to Azure. And now I work with diverse set of tools, including Azure Machine Learning Service. It's well, Azure Machine Learning Service and Azure Synapse Analytics, which I'm going to use for demo purposes during my talk. But let me start with a question. Please raise your hand if you think that there is at least 10% risk that AI will take over our humanity or society. Almost nobody? A few hands? Okay. This is not the main topic of this talk, by the way. If you want to know more about the social aspects of AI, I strongly recommend to watch the AI Dilemma. The links are here. By the way, you will find a set of useful links on my presentation, and they will be all available for you later for sure. What I'm going to talk about, because responsible AI is a vast and complex topic, so during this talk we will focus on two key aspects: how to handle your data and your models, not only for optimal performance, but also for fairness. And because we have like 30 minutes, more or so we will focus on audit part. But feel free to ask questions about how to implement those rules or best practices. To provide some context, I will briefly discuss responsible AI principles and two methodologies: team data science process and model development process. Hopefully there will be time for questions and answers. If not, feel free to ask me later. So principles of responsible AI. AI system must treat all individuals fair. That's it. And we are going to talk about this mostly during the session. To build a trust, they should work reliably and safety in conditions. That's slightly out of topic. They should adhere to privacy regulations, for sure. They should work more or less the same for everyone. That's inclusiveness. And if AI systems are part of decision-making processes, they can severely impact human lives. Going back to my first question. And if so, individuals should be able to understand, at least partially, reasons why the decision was made like that. This is transparency, and we can achieve this via explainable AI. And there will be a few slides about explainable AI on my slide deck at the end. And that's the crucial point. I think that data scientists, so designers and builders of AI systems, should be held responsible for predictions, for actions taken by their systems. I mentioned two methodologies. The first is team data science process. Probably some of you are familiar with this kind of methodologies. The point is there are different stages, and those stages are taken iteratively. Again, useful links if it's new for you. Team data science process is an extension or is built on top of cross-industrial standard process for data mining, CRISP-DM. The methodology that I learned 25 years ago, it's still valid. And a few words about each of those stages. The first stage, business understanding, aims to, understand, to business objectives and goals. The second, data acquisition, involves, well, acquiring data and explanatory data analysis, let's say. The third one, modeling, is all about developing and improving model performance. It's only one of those 5 stages. Do not focus on modeling. A lot of people, unfortunately, do. Then there is the deployment. The deployment involves, well, deploying the best or good enough model to production. And the final stage is customer acceptance. The goal of this stage is to gain an acceptance from end users. As I said, TADSP was built on top of CRISP-DM. Another extension of CRISP-DM is model development process introduced by Przemysław Biecek. The key idea here is that the resources needed during the subsequent iterations are different because we gain some knowledge during the previous phases, and now on subsequent iterations we can allocate those resources in slightly different way. Furthermore, I think that any talk about explainable AI would be complete without mentioning Przemysław Biecek's work in this area. So that's the opportunity to have a look at one more link. If you are not familiar with his work, maybe it's, well, I do strongly advise you to check it. And now we can move to the main topic of this presentation. As a data scientist, you should know how bias can be incorporated and how bias can influence predictions made by your models. Why? Because bias is the main and the most common reason of unfairness. Which means that you should do this data audit, data balance analysis as one of preliminary steps during each of data science machine learning projects. If you do, you can save a huge amount of time, not only your time, but also GPU time, by finding some, well, imbalances, some mistakes, data quality issues that will have to be fixed sooner or later. So sooner is better. Data balance analysis is also great for debugging, end-to-end debugging of machine learning models. So what this data balance analysis actually is. And I will use an example. As we are talking about fairness in context of Azure machine learning models, it will be good to define what we mean by fair model. So let's assume that we built a classifier that can classify citizens and individuals into 2 classes, those who earn more and less than $50,000 per year. So those kind of models are usually trained based on individual profiles, like age, gender, race, income, debt, whatever else. Let's assume that this classifier will assign more or less 75% of citizens to the negative class, which means less than $50,000 per year, the income. However, upon investigation, you notice that non-white citizens are slightly lower chances to get a positive prediction. And this should raise a question. How can we ensure that this model is fair? That this model treats fairly all individuals regardless of their race, sex, and maybe you can think about some other sensitive variables. This visualization, maybe you are recognizing this visualization. This visualization is provided by Azure Machine Learning Service. If you just register a dataset, you will see something like that. And maybe you also recognize the dataset. It's based on census dataset, adult census dataset that represents data collected by during the US census in 1994, I think. So now we are talking about data audit and data balance analysis. Data balance analysis contains three types of metrics. The first are distribution balance measures. There are a set of measures, actually. And distribution balance measures will allow you to compare your dataset distribution to a base referential distribution, like uniform distribution. It's pretty easy and fast to compute. Here, I switch to Synapse Analytics, and to be more precise, I use the SynapseML, so a library included in the Synapse Analytics that you can install in different platforms as well. The SynapseML is a tool built to enhance Apache Spark into different directions, including scalable deep learning, stress-free serving, and most importantly, large-scale data interpretability, or, well, explainable AI, let's say. So what I did, I compute a set of distribution balance measures. Let's focus on this one, Jason-Shannon distance. Why not? And we can see that Jason-Shannon distance for race is 0 point, and for sex is 0.1. This measure is on a range from 0 to 1, where 0 means perfectly balanced distribution. So based on this, we can conclude that the sex is way more balanced in this dataset than race. Hence, some races are underrepresented and others are highly overrepresented in this dataset. That's the fact. Yeah? We are talking about distribution balance measures here. But you can do more. The second set of measures that you should, well, use are aggregate balance measures. And they are calculated. Maybe you spotted that those two metrics were calculated independently for both sensitive columns, for race and sex in my case. Here, with aggregate balance measure, you will get a metric calculated based on all those sensitive variables at once. If we have two variables, sensitive variables, the metrics will be calculated for all pairs. And for each pair, you will be able to check if the inequality. So how often in your data set, the combination pairs like black woman or white man or Asian Pacific Islander woman are present. Slightly deeper understanding and better view into inequality, hence bias, that can be observed in your data. In this case, I compute this Atkinson index. Atkinson index for my dataset, for the census dataset, is 0.78, which you can interpret as an information that roughly 78% of observations, data points, should be removed from this data to achieve perfectly balanced dataset. So it looks like, in terms of those two sensitive variables, race and sex, the dataset is highly imbalanced, almost close to perfectly imbalanced dataset. What should we do at this stage? Even before we will start modeling phase. Well, we can think of some actions like removing some overrepresented combinations or adding those that are underrepresented. In this case, probably it will be not a good idea, but think about synthetically generated data or a specific sampling mechanism that you should incorporate even before you start modeling. And there are one more type of measures, feature balance measures. You noticed that the first two were computed based on features only. Features mean input variables, yeah? Explanatory variables. Feature balance measure are computed based on feature and label. Features and label, and a label. And with feature balance measure, you can check if all combinations of your sensitive variables, again, sex and race in my case, will get the positive outcome, less than 50,000 per year, at the same rate, at constant rate. The feature balance measures are commonly referred to as parity, by the way. And for this data set, it looks like that. So we didn't even start modeling, and we can already set the ground true for this fairness. If you remember, the main question was, how can we ensure that this classifier treats all citizens fairly, regardless of race and sex? It doesn't mean that we are all the same. Maybe younger people tend to earn as less. It's a fact that should be visible here. So the goal is not to try to, well, remove all inequalities. No. The goal is to remove inequalities that are not visible in data, and firstly, to be sure that the data set used for training correctly represents the wide variety visible in a society. Yeah? If it's like that, okay, we can proceed. So looks like, actually, in this case, if the race is white, it's a slightly higher. If you're white, you have slightly higher chances based on, well, statistic that you will earn more than 50K than if the race is American Indian Eskimo, for example. And that was the first part, data audit. Now, let's move to the second part. So the model interpretability was in the area of interest since the very beginning of statistical modeling. And in this respect, we can generally divide machine learning models into two categories, black box and glass boxes. Black box is a model that is hard to explain because a number of parameters or complex structure. Glass box is the opposite, is the model that can be relatively easily understood by data scientists and users. And our goal is, so we can always switch from black boxes to glass boxes and we will get interpretability. But probably we don't want to do this because simpler models not always can be applied. We can lose performance. So our goal is to find techniques that are model agnostic, that will allow us to interpret any black box model without changing its structure. And there are two types of explanations as well. We have global explanations. They are aimed at the average prediction, so let's say model performance, and based on the whole data set. And local explanations that can be used to interpret predictions in terms of features, input variables for a specific data point. Why the model said that this person will earn more than 50K. Not on average, but for this specific data point. And I'm going to show you some methods that you can use to globally and locally explain models. Let's start with partial dependency plots. But even before, if you remember those methodologies, during the modeling phase, we train a lot of models. And then we choose the best one based on some performance metrics. Again, Azure Machine Learning Studio, I train a classifier. That's the, let's say that I will focus on accuracy, 86%. That's my primary metric. And now it's a pretty complex model, pretty complex function that I am going to describe using a single metric, single statistic, accuracy. Isn't that an oversimplification? In my opinion, yes. And if this model will be used as a part of decision-making processes, probably you really would like to know why the model, how the model works. Maybe, if not for fairness, just for improving performance, because with this you will be able to debug and improve the model and improve its performance. So my point is, yes, we have to choose a model based on a single metric, but then we can do more. And what I'm showing you right now is a responsible AI dashboard. The responsible AI dashboard combines a set of tools. It's a part of Azure Machine Learning Studio, Azure Machine Learning Service, by the way, as you can see. Those tools allows you to do model performance and fairness assessment, error analysis, data exploration, and more. What's very nice, you can define cohorts based on any logical expression. So you can divide the data into subsets, those cohorts, and a good starting point is to check the performance of your models for not only for the whole data set, test data set, but also for specific cohorts. You may find something like this. So that's the all data. At the top, we have a raise not equal to white. The recall is 0.46, while the overall recall is 0.6, and the recall for white citizens is 0.65. Is it good? Is it bad? Should we start to worry about this? Well, let's check. This AI set, as I said, responsible AI dashboard sets the dashboard set of tools. So that's the second tool, Dataset Explorer. Dataset Explorer is great if you want to just visualize your data or display some statistics. But as you can see here, you can also use predictions, like classification outcomes on those charts. So now we are observing the distribution of classification outcomes per race. And maybe you noticed that the type 1 error, so false positives, were made by this model only for white citizens. Is it good? Is it fair? That's the question. Perfect. Because all those things that we are seeing right now should be correlated, yeah? Should be, with the insights we got during the data audit. So just by watching the data, we can probably predict this problem without even training the model or set of models and choosing the best one, because now we can see it's actually not that good and we can start over. Yes, this race is overrepresented. Absolutely. So, probably all of you are doing this data balance check if you are building a classifier, especially binary classifier. But the point of the first part of this talk is that do this data balance analysis not only for a label, but also for features, especially sensitive features, or features that you think might be important in this case. Thank you for the question. Okay, there are visualizations, but there are, of course, also metrics that you can compute. Because if we have a metric, a number, we can automate some processes. And the first technique that I strongly recommend you should start using if you are not doing this right now is to compute those partial dependency plots or profiles. And based on this, you will see the prediction, so the output of the model, as a function of chosen feature. So if the value of this feature will change, how the prediction will change accordingly. Great for debugging, crucial for bias and unfairness detection. In this case, it looks like that. So again, SynapseML used here, and the ICE transformer. To build this transformer, you have to provide a pre-trained model, point to a label, so the output, in my case, probability, set the kind to average, why I will explain shortly, and then provide those features, categorical and numerical features as well. And you will see something like that. And based on this, we can set that on average, it's a global explanation technique. On average, American Indio Eskimo race is, for this race, if the race is like that, the average prediction is lower than for other races. So, if you don't set this kind to average, by the way, though the PDP profiles are based on ceteris paribus profiles, and now we are going to talk about local explanations starting with ceteris paribus profile. And in SynapseML, you can compute them using, well, individual condition expectation plots. So another the same transformer, but differently configured. The difference is that now you will get this profile, so how the prediction will change based on the feature value changes, but not on average, but for a specific data points, for specific observations. So it may look like this. To improve the readability of this plot, I limited number of samples to 50, but the rest is more or less the same. And now you can see that for those 50 samples taken randomly from this DF data frame, so trained data frame probably, the lines for this American Indio Eskimo race tends to be closer to the center. Hence, the probability of positive prediction is lower, the same as on the aggregate plot, the same story. Those techniques are pretty cheap, so you can compute them quickly. But if you want to interpret the model predictions, probably the best model, so now we know the model is good enough, not only in terms of performance, but also as we are talking about the fairness. So maybe it will be nice to add explanations, to build an explainer for this chosen best model. And there are two techniques that you can use. The first are shapely additive explanations based on shapely values, introduced in 1953, I think. They're based on cooperative game theory. In this cooperative game theory, they are solving a very hard problem, actually, interesting problem. If there is a cooperation, so a group of people that are going to achieve a gain and achieve this gain, how to distribute this gain among all those contributors fairly, as they may be play completely different roles. And we can apply this concept to machine learning. So here, a contributor is a feature, so a variable, a model is a cooperation, and model predictions are gain. This payoff. And the task in hand is how to distribute this payoff, those predictions, among features. So which feature contribute the most to the prediction? And if you think about this like that, you will notice that you can do this by permutating features and training a lot of models and comparing those models' predictions. So yes, we can do this. But maybe you notice this additive part of the name. It's pretty important because if the model is linear, like logistic regression or linear regression, the order of those parameters doesn't matter. But most commonly is not the case. So now, well, how you can compute those shapely additive explanations for nonlinear models, and the basic idea is that you can compute them multiple times for different cohorts, and you will change the order in which you are adding or removing variables per cohort randomly, which sounds expensive in terms of time. So it will grow pretty quickly the number of features. We can minimize the number of trials by using the kernel HAP approach. It was described in the paper Unified Method for Explaining Model Prediction, I think. So you can do this, but still it's pretty expensive if you are not working with tabular data, if there are many input features. So in this case, the state-of-the-art approach is to use LIME, locally interpretable model agnostic explanations, which works by generating artificial data, perturbing the observation that you are interested in, and reducing dimensionalities, hence super pixels if you are talking about images, and then training a simple glass box model on top of those artificially created observations, and use this model as approximation around the observation in hand. So the point is, Lime will give you explanations if you are working with texts or images. But this way or another, you will see something like that. So aggregate feature importance, and now it's obvious that the marital status followed by age, capital gain, education, then occupation are important for this model to predict if a person will earn more or less than 50K per year. And you can do this for a specific data points, so individual feature importance. So again, I choose a false negative, and now my question was, why the model make this mistake for this specific person? And of course, individual feature importance can be different. In this case, it was still marital status, ages, capital gain, but then sex and race. They may differ from global feature importance. Of course. And yes, we are running out of time. The conclusion is, when you invent a new technology, you uncover a new class of responsibilities. As a data scientist, we should be responsible for our model predictions. And the most common and not that hard to correct mistake is actually the reason for the unfairness is a bias. You can detect bias in data, and you can detect inequality or unfairness in predictions using those techniques I presented. There are also techniques to mitigate this bias, but we have no time to discuss them. Questions?
Before the questions, bravo. Yes, please. I do understand we're after the time. No, exactly at 12:20. Any questions or comments? Okay, maybe between the sessions, maybe during the lunch break. Marcin, I would like to congratulate you. It was great. Thank you.
Thank you. And all those resources will be available, as you can see here in my presentation. Thank you very much for your time.
Thank you. Next presentation within 10 minutes.